So in this video we're going to find the derivative of e to the 2t sine 5t using Laplace transform. Now our function here, e to the 2t sine 5t. Let's just write that down to start with. F of t is e to the 2t sine 5t. Now in previous videos we've gone over this one a few times, so check the link below. I'll show you how we come about this result. The Laplace of e to the 2t sine 5t, that will give me a result of, so it's 2t in exponential, so I've got s minus 2 squared, that takes care of the 2t in there. And then for the sine part of things, what I need is, the input for sine is 5, so I've got 5 squared and then 5 in my numerator. Now the generic form of that, of the Laplace of e to the at sine bt, that will give me b over s minus a squared plus b squared. Okay, so that's the generic result. If you check the link below, you'll see how this comes about. Okay, now we need to find the derivative of this. So it's all well and good we got this, but what there is a generic result for derivatives using Laplace. Now what we can do is the Laplace of f prime, that comes about by having s times Laplace of f and minus f at 0. So that's got nothing to do with the Laplace there, we just evaluate it at 0. Here we've got the Laplace of f, and here we just multiply it by s. So our Laplace of our function is this, and we need to evaluate it at 0. So I need to evaluate this at 0, and then multiply our Laplace result by s. So let's go straight into the lat. So the Laplace of f prime, that equals s times our Laplace of our function, which is this. So we've got 5 over s minus 2 squared plus 5 squared, and then minus e to the 2 0, so minus e to the 2 times 0 sine of 5 times 0. Okay, well this we can take care of. We'll just put the s, I'll make that clear as it's an s, it's not a 5. We'll just put the s in our numerator here. This is e to the 0, which is just 1. And this sine of 5 times 0, that is just 0. So this will cancel out. So now we're left with 5s over s minus 2 squared plus 5 squared. So now here we've got something different to our generic result here, b over s minus a squared plus b squared. We've got an s in our numerator. So this leads on to the next generic result that we're going to need to use. So e to the at cosine of bt, this will give us a slightly different result. This one, what we need is s minus a over s minus a squared plus b squared. That will give us our generic result for this cosine version of e to the at. So how are we going to get that into this kind of format? Well, here we've got a is 2, so let's just write that down, a equals 2. We've got a b which is 5, so b is 5. So let's get an s minus a in the numerator, and let's just manipulate that a little bit. So s minus 2, and then we've got s minus 2 squared plus 5 squared. Now we've got this 5 yet to use, so we can put this 5 here and multiply that. That will then give us back our 5s. But now we've got 5 times minus 2, which is minus 10, so we've gained a minus 10. So now what we need to do is add 10. So if I do that, this will then give us the same value as this, and it's in a format that we can maybe use for this. So let's just simplify this out now. So now we've got 5 times s minus 2. What I can do is I can now break this apart. So now I can write 5 times s minus 2 squared plus 5 squared. So I'm going to effectively break this fraction apart. So I'm going to have this bit and this bit. So now I can add 10 with my same denominator. So now I've got 10 over s minus 2 squared plus 5 squared. Okay, now we've got something now that looks a little bit more like what we want with this and this. So s minus 2, 5 minus 2 squared plus 5 squared. So that's going to give me, using my generic formula here, s minus 2. So that's going to give me e to the at. So I'm going to have e to the 2t. And then s minus a squared plus b squared, cosine of bt. So now I've got cosine of my b squared. So here I've got 5. So cosine of 5t. But I've got a 5 here. So I need to multiply all this by 5. So that would take care of that. 5e to the 2t cosine of 5t. Okay, now what about this one? I've got a 10 on. So what I can do is I can take the 10 out. So if I just take this bit here and write that as 10 times 1 over s minus 2 squared plus 5 squared. Now ideally what I want here, using this, because I've got a constant here, no s's, I need to have a b in my numerator. So if I change that 1 to a 5, I've now got the b in the numerator. But as I've gained an extra 5 here, hence multiplied it by 5, if I divide it by 5 on the outside, I've got the same result. So now I've got 10 over 5. So then that would give me my e to the at sine bt, but I'd have to multiply by 10 over 5. So now what I do is I add 10 over 5, that's 2. And then 5 over s minus 2 squared plus 5 squared, that's going to give me e to the 2t sine 5t. Okay, now would that be the derivative of this? Well, using the product rule, I've got to break this apart. E to the 2t, derivative of that is 2e to the 2t and then sine 5t. Check, that's all good. And then if I take the derivative of this one, sine 5t, well that will give me cosine 5t, and then by the chain rule I'd have to multiply by 5. So then I've got 5 e to the 2t cosine 5t. And that's what I've got there. Check. So therefore, that is my result by Laplace transform. Okay.